once we started to develop a bit more with some like superbike style cams, a lot more lift duration, we were sort of seeing about that 430, 440 horsepower. I think fully assembled with flywheel and alternator and starter, it's 96 kilograms. So it's a pretty power dense little unit.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Simon Longdill from Prototipo and Synergy right here in little old New Zealand. I actually had the pleasure of meeting Simon many years ago because I had the opportunity to tune one of his bespoke Synergy V8s, and this is a thing of beauty. Simon wasn't happy with the available options when it came to 2.4 litre engines for use in a Speedway midget, and looking at the rulebook decided that there was nothing to stop him making his own. And that's exactly what he did. He took a Kawasaki ZX12R cylinder head and barrels, or actually two of them, and then crafted his own bespoke billet CNC machine crankcase and a custom crankshaft to make a 2.4 litre V8. And suffice to say, it worked exceptionally well. This car was competitive here in New Zealand, and it was also competitive in both Australia and the US, enough so that at the Chilli Bowl in the United States, it was actually banned from competing the following year. Now, that was all some time ago. The Synergy V8 has grown up, and Simon's also adopted more modern motorcycle cylinder head technology, building a 400 plus horsepower 2 litre V8 for use at Bonneville, where it claimed several speed records. In this interview, we dive deep into Simon's background, how he formed this love of engineering and engine building, and how he's turned this into a business. We also find out why Simon saw fit to create a bespoke plug-and-play engine package for the Toyota 86 and Subaru BRZ, and we get his take on the future of production engines and fuels, specifically hydrogen, synthetic fuels, and electric vehicles. Before we get into our interview with Simon, for those who are new to the Tuned In podcast, High Performance Academy is an online training school. We specialize in teaching people how to build performance engines, how to construct wiring harnesses, how to tune EFI. We also cover topics on 3D modeling in CAD. We cover race car setup and development and race driver education, just to name a few. All of our topics are covered via high-definition video-based training modules that you can take from anywhere in the world, provided you've got an internet connection. This gives you the benefit of being able to learn at your own pace and at your own place. All of our courses also come with a 60-day no questions asked money back guarantee, so if you take a course for a test drive and decide it wasn't quite what you expected, no problem. Let us know, you'll get a full refund of the purchase price. If you do want to find out more about our courses, then you can head to hpacademy.com/courses for a full list of our courses. We'll also put those in the show notes. And as a podcast listener, you can use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. Lastly, if you like free stuff, well, have I got a deal for you. If you head to hpacademy.com/giveaway, again, that link will be in the description, you'll find our latest giveaway. We change these up every month or so, and we partner with some of the biggest names in the aftermarket performance industry. One month it might be an aftermarket ECU or a power distribution module. It could be a dash logger. It could be a set of corner weight scales, or essentially anything in between. Suffice to say, it's going to be a great prize. There is absolutely zero catch, no purchase required. Get your name into the draw. The winner gets this prize shipped to their door, regardless whereabouts they are in the world. All right, let's get into our interview now. All right, thanks for joining us today, Simon. Let's start, as we always do, by finding out a little bit about your background and specifically how you developed an interest in cars and, more in your case, engineering.
Yeah, probably like a lot of your listeners and people on the podcasts, just always interested in things mechanical and cars, things that made noise and moved. Yeah, just played with lawnmowers, just pulling stuff apart at home. Motorsport events. I remember one in particular, the Wings and Wheels Festival I used to have up at Unequal with all sorts of aircraft and racing cars. And I think there was an old Lotus Formula One car with a Cosworth DFE in the back of it, and just the sound of that thing screaming up the runway just moved something inside. And it's like, all right, I need to be knowing more about what makes that sort of noise and make something go like that.
So what was your sort of qualification path from here to sort of get you to where you've got to today?
Pretty normal, really. I was sort of reasonably good at things like maths and science at school, as well as sort of wanting to be hands-on and just loving playing with stuff. That led me into doing a degree in engineering at University of Auckland. That was mechanical engineering. Really enjoyed that. Got to the end of the degree, actually my fourth year project, I was sort of lucky enough to have an involvement in a motorcycle engine design program.
Okay.
There was a company in New Zealand, Buckley Systems, developing a 500cc Grand Prix racing motorcycle to go and race in the World Championship, which was a pretty sort of optimistic undertaking, but that's the attitude was there and the belief that it could be done. So that was quite pervasive. So my fourth year project, I actually did a bit of work on the configuration of that engine, the balancing, the crankshaft arrangement, which was a little bit novel in that it was a 3-cylinder engine in a V configuration. So we looked at different V angles, firing orders, balance shafts, developed a bit of a method there.
Just coming back before I let you go on there, that Bachelor of Engineering degree in mechanical engineering, that's a very broad degree. It's not sort of motorsport centric by any stretch of the imagination, is it? So can you decide this project, working with this engine, this fits nicely for your fourth year project requirements, or had you already sort of gravitated more towards the engine side of mechanical engineering at that point?
Yeah, I think it's just my own personal interest. I was already, trying to modify cars and build engines at home in the garage. The study at university was a really neat counterpoint to learn some of the theories behind the practicalities. So you've got a lot of optional subjects you can choose and really sort of focus where your studies go. Nothing specifically motorsport related, but you probably end up tending towards the material sciences, your aerodynamics, your thermodynamics, those sort of studies, which is what I did.
The other thing I'm interested in here is New Zealand is a very small country, and we've got essentially no automotive or motorsport base. It's not like the UK where there's Formula One teams you're going to chip over left, right and centre. What did you sort of see for yourself at this point in terms of a vocational direction?
I guess I really hadn't thought that far ahead. I was just following what I was interested in, and I guess it's the philosophy that, hey, if you're interested in something, you study hard, you do well at it, then the opportunities will present themselves in some form. You just have faith that will happen. And luckily enough, in my case, it has worked like that.
I think you did right there. And another sort of thing that's really easy to overlook, I mean, I'm not quite sure what age we're talking here, but I went through a 4-year university degree, Bachelor of Technology, majoring in product development. And I think at that age that I was going through that degree, it's sort of almost farcical to think that you're going to know the full roadmap for what your life's going to look like for the next 20, 30, 50 years. It's just ludicrous, and sort of almost think kids coming out of school these days and going to university, it's difficult to know what to sort of advise there in terms of, you can't pigeonhole yourself into a certain career necessarily because you don't even know what you don't know at this stage. So I think you're right there. I mean, following a passion and then being open to, what the universe provides essentially, I think is a pretty smart approach, which clearly has worked for you. Let's continue with your sort of tertiary education anyway.
Yeah, so completed my degree, which was great. Did a little OE after that, but I guess I enjoyed the study. Sort of had unfinished business, and I had the opportunity with the company I was doing the motorcycle work with. They wanted to develop some more sort of R&D and develop some more technology that would basically improve their racing motorcycle. So I had the opportunity to carry on and do a Ph.D. at the University of Auckland straight afterwards. At that time, you could basically skip the masters and go straight into a Ph.D. and you had a review after a year or two to make sure you were on track and meeting all of the targets, so you could save a little bit of time.
For those who aren't sort of up to speed with what a PhD entails or tertiary education in itself, could you give us a quick sort of overview of what a PhD actually means and what it involves, I suppose, more importantly?
Yeah, basically you're undertaking a big research project that really has to be novel. You're basically trying to solve a problem that no one has solved before. Typically, it'll take 4 to 5 years of reasonably intensive study, theoretical, practical, often experimentation, development, and then a big thesis report that gets written up at the end of it. And then you have to basically defend your thesis they'll have some overseas examiners who are really experts in that field come over, give you a pretty stiff interview process in terms of figuring out if you really know what you've been sort of working on for the last 4 years. And after all of that, you'll get awarded your doctorate or your PhD.
Okay. Can you again give us maybe a short version of what your PhD involved with this company? What sort of novel aspect were you researching and sort of experimenting with?
Yeah, what we were looking for was, I guess probably what we take for granted now is, measuring the air-fuel ratio on a 4-stroke engine is quite trivial now. We've got really good wideband sensors, the controllers, they're quite fast, they're accurate. The problem with the 2-stroke engine was that because of the dynamics inside the engine, you've got your intake port and your exhaust port both open at the same time. You end up losing quite a significant part of the fresh air intake charge out the exhaust port every cycle. So having a lambda sensor or really technically a sensor for measuring unburned oxygen in the exhaust pipe of a 2-stroke really doesn't tell you much at all. It just tells you how much of the fresh charge you've lost through on the overlap period. So there really isn't a very good way of getting an accurate high-speed measurement of the air-fuel ratio of a 2-stroke engine. So that's the problem we were trying to solve, is look at all the different ways in the world that we might be able to come up with a system to have a really fast, accurate measurement of the air-fuel ratio. After going round and round and looking at the different ways we might want to do it, we settled on putting a fibre optic probe through the combustion chamber of the engine, taking a signal, of the light emission from the flame front. And there's certain characteristics of combustion that, depending on the ratio of air to fuel, various wavelengths will either be higher or lower. And so using some quite sensitive instrumentation, we could basically detect the air-fuel ratio from the colour of the flame, I guess would be the nice way of putting it.
That's incredibly interesting. I need to dive a little deeper into this because 2-stroke engines is something I have never really had the opportunity to deal with, at least prior to being a kid and flying radio-controlled planes, but I don't think that really counts in the context of this conversation. I do understand that measuring air-fuel ratio with a lambda sensor in a 2-stroke engine is problematic for all the reasons you just said, and I think what you touched on there is just important to reiterate, is that lambda sensor doesn't actually measure fuel. It measures unburned oxygen in the exhaust gas. And I know that a lot of novice tuners will get tripped up when they're tuning a car that has an ignition misfire. I'm talking here 4-stroke. Because when you have a misfire, you get a full cylinder's worth of unburned fuel and air passed into the exhaust. And the key point here is unburned oxygen goes into the exhaust. So when you actually have an ignition misfire in a 4-stroke engine, that will read lean on the lambda sensor. And again, I know that confuses people because it doesn't really compute. They're sort of thinking that it's measuring your air-fuel ratio, but it's not quite that straightforward. Let's come back to 2-stroke engine tuning. My understanding is that EGT forms a big part in sort of optimizing the mixture in a 2-stroke engine, or has traditionally. Is that correct, or am I a bit off the mark there?
No, you are correct. And look, I certainly don't profess to be anywhere near an expert in sort of modern high-performance 2-stroke tuning. But typically, you'd be looking at EGT. Reading the spark plug is still well practiced, and probably more common now would be piezo sort of under spark plug washer, and you're actually looking at sort of detonation counting really, and you'll have a tolerable level of activity from the piezo sensor under the spark plug to run on a certain degree of knock threshold.
So that's interesting. Are they using that purely for knock, or are they using that for air-fuel ratio and knock? Because obviously there's an interaction here. I mean, you can create a very lean mixture with conservative ignition timing that won't knock, or alternatively, depending, if you're knock limited by your fuel, you could have a safe air-fuel ratio, very advanced ignition timing, and still be on that knock threshold.
Yeah, absolutely. And that's sort of probably where the EGT comes into it, working out sort of how rich lean you are. You'll have some knowledge of what your optimum ignition timing should be, so that probably doesn't change as much. But often they're just jetting or adjusting the fuel in for the atmospherics on the day.
Okay. Just given that I'm assuming that this project was done a fair while ago now, how has the industry reacted to it? Obviously, 2-strokes are kind of a fringe engine technology now with problems with emissions compliance, but they are still around. Has anyone else sort of taken on that technology that you developed at the time, or has there been an alternative direction for air-fuel ratio measurement?
No, I think you touched on it. I mean, at the time, To put it in context, this was probably late 90s, early 2000s, so over 20 years ago now. We weren't sort of blessed with the level of miniaturization of things like computing hardware, miniaturization of sensors. We developed basically a rack-mounted data system that could take the signal from a pressure transducer in the cylinder, the fiber optic, the light emission from the flame, up to 12,000 RPM, taking a sample every crankshaft degree, which was quite sophisticated back in the day. But we really struggled then to, okay, how do we miniaturize that, put it into something that could be an on-vehicle type thing and have the processing power to do a control strategy in real time using it.
So you're using this technology more for dyno development and validation as opposed to something that's actually going to be on the motorcycle?
Yeah, absolutely. Yeah, so that's the sort of the roadblock that we got to. So really the research has sort of been done. It's there. Love to have the opportunity to sort of pick it up and with the advantages of modern technology now and see where we can go with it. And that may happen in the future, but certainly at that point we didn't carry on with that further.
Yeah, okay. Again, my knowledge on two-stroke engines is really quite limited, but obviously you've got a power stroke every 2 crankshaft revolutions instead of every 4. So on face value, it seems a no-brainer that for a given capacity, they're going to be able to make more power than a traditional 4-stroke engine. As I understand it, the emissions is the real problem with a 2-stroke being viable as a modern alternative. Is that the case? Is there any potential to these engines? Are they dead in the water, or should I start learning about them?
No, I think you're right. I mean, back at that point, they were rapidly going out of fashion because of the problems with the emissions, especially for a typical crankcase scavenged 2-stroke. You're ingesting in air and fuel through a carburetor or some similar device that's being put through the cylinder as a homogeneous charge, and you're losing a big percentage of it straight out the exhaust pipe. So your hydrocarbon emissions are just off the scale. They were always going to be on a sort of losing battle with the modern emissions technology. That said, when you look at the basic efficiency of the platform, like the most efficient engines sort of in operation now are these big container ship engines, these big crude oil bunker fuel powered, massive, measured in sort of cubic meters of capacity rather than litres. But they're well over 50% thermal efficiency, and they're basically a uniflow 2-stroke engine. They're all 2-strokes with the benefit that they've got direct injection. They're injecting the fuel after all the ports are closed. Different porting arrangements. They've got combinations of cylinder ports plus poppet valves, so the flow is sort of going basically just one way through the cylinder. And with a direct injection, you're sort of solving pretty much all the problems with the raw fuel escaping out the exhaust pipe. So it is interesting that in the time that the 2-stroke engine's gone out of fashion, a lot of the technologies that would most help it have really come into play on the 4-stroke engines with the advances in direct gasoline injection and the modern sort of control strategies around that. So certainly not beyond the realms of possibility that 2-strokes will have another go round in the future.
Your point there about the direct injection fixing a lot of the problems with the port timing is definitely valid. I can only assume there, though, the engines in these massive ships are running at essentially steady state conditions and at a really relatively low engine RPM compared to what we're used to for a road going vehicle. So I don't know if that would become problematic. The efficiency you talk about there, I just wanted to touch on that as well. 50% efficiency. What you're essentially talking about, if I'm reading this right, is how much of the energy contained in the fuel is actually being converted to power. Very wasteful in an internal combustion engine, no matter what it is, but the rest goes out in terms of heat and sound. As I understand it, your sort of modern road-going engine, something pretty efficient, and modern's going to be probably in the region of about 35 to 40% efficiency, whereas the best of the best, Formula One, I mean, very hard to pin these guys down, but that's sort of quoted at around that 50% mark. Do those numbers sort of stack up with what you expect?
Yeah, that's certainly correct, and probably worth noting that when they sort of quote these peak efficiency figures, that's typically going to be at one operating point as well, which might be sort of steady state cruising down the motorway at 50 miles an hour, sort of 80 kilometers an hour, where everything's good. But obviously, if you're stuck in traffic with the car idling, your thermal efficiency is basically zero because you're burning fuel and not going anywhere. So it could be anywhere between there and your peak, depending on what you're doing.
And just for full context, because we will come back to this topic in a little bit, if we compare that to electric vehicles, typically sort of in the 90% efficiency, correct?
Yeah. When you're looking at your transfer, your storage, your conversion losses, you certainly be in the 90%. So it is a pretty smart way of getting energy around.
Interesting little diversion on the two-stroke front, but let's get back to our topic, which is your own development of your own bespoke V8 engine. Can we fill in the blanks between where you are now with your business Prototipo, which also encompasses the Synergy brand, and where you sort of left off that two-stroke project for your Ph.D.?
Yeah, so I had a sort of career sort of really outside engines for 6 or 7 years, working on sort of semiconducting manufacturing equipment, sort of big electromagnets, while being also sort of involved a little bit in the motorsport, but more as my own hobby, building cars, building engines, modifying things, playing with different sort of early engine managements and turbocharging. Got involved in Speedway racing here in Auckland, which is like a dirt clay track, typically from a quarter mile up to a half mile. Quite a famous track, Western Springs, here in Auckland. Involved in some teams sort of helping drivers as on the crew. Had the opportunity to build a car and drive a car for a few seasons, which is a lot of fun. And the cars we were building then were just using the little 3SGE Toyota twin cam 2-litre engine. It was around trying to develop an entry level class for people to get into this speedway racing, where typically the other options for engines were your American sourced, like half a V8, 166 cubic inches push rod, or like the Esslinger, a Ford Pinto based, big purpose built, midget racing engine. So we raced the little Toyota 3SGE for a number of years, and we were always really surprised by how well it went for what it was. It was always quite easy to drive. Power delivery was very smooth. Didn't have a huge amount of torque or power, but being a nice modern twin cam engine, it had a really sort of broad and easy to use power delivery. So sort of that got us thinking as we sort of went on, and I guess our aspirations got higher, and we were trying to get more and more competitive. The rules allowed us to run a double overhead cam 4-valve engine at 2.4 litres instead of what we were doing, which was 2. And so we just kept thinking, man, we're going okay with 2 litres. If we had 2.4, we'd just be like all over it. We'd be really competitive. Searched around, said, okay, how do we get a 2.4 litre engine into this thing? When we sort of looked at the 4-cylinder automotive engines that were potential donors, and just sort of went back to fundamentals. What's the bore size? What's the stroke? What can we sort of rev the engine to? What's the typical BMEP? What sort of power at that RPM can we then expect? Nothing really stood up because they all became quite long stroke. You couldn't rev them. The potential power was just going to be limited.
I'm just going to actually interrupt you there. You mentioned a term that I don't think's popped up on the podcast before, BMEP, brake mean effective pressure. This is something we hear when we're comparing different engines around. What's that term actually mean, and how is it useful to you?
BMEP is a good way of comparing different engines for their basic efficiency. It really takes the engine capacity out of the equation. So you can compare a 1-litre 3-cylinder engine with a 6-litre V12 engine. They're both making different power levels, but based on the BMEP, you can see which one is more efficient or the better engine. It's basically it's a torque per litre, basically, would be the simple way of explaining.
So it just normalises the torque and takes capacity out of the equation.
Normalised with the engine capacity, so you can get a sort of a good comparison. We knew that what a BMEP figure for a well-developed sort of motorsport engine should be, and then that's going to set what the torque is if you know your capacity, and then if you know what RPM you can run the engine to and the BMEP, then you can predict roughly what sort of power that you should be expecting from it.
So the problem you were seeing when you started looking at larger capacity 2.4 litre 4 cylinders, let's say 4G64 would be an obvious example of that, is just the inability to rev these engines hard enough because of the longer stroke.
Absolutely. Typically all of those automotive engines that went to 2.4, they weren't doing it to get a lot of power. They were doing it drivability, low down torque. The bore stroke ratio was getting very under square, which is not really what you want for a high performance racing engine. So then we sort of hit up to the idea, okay, what if we just added more cylinders? We get to 8 cylinders. If we had a pair of 1200cc engines, what's that going to start to look like? As soon as you're into that 1200cc sort of range, suddenly you're into motorcycle type engines. You're not stuck with an engine speed of 7,500, 8,000 anymore. You've got engine speeds of 12,000 RPM. If you're looking at 8 cylinders, you've got much more intake valve area. Your bore to stroke ratios are much better. Suddenly, it's sort of, when you look at the predicted power you can get from 8 cylinders versus 4, it's a lot more.
So this really comes down into the equation for power, which is where we're multiplying our torque by RPM and then dividing it out by a constant. So the key really, if we want to make large amounts of power, is that we want to make torque at very, very high RPM. And as you say here, these motorcycle-based engines can rev to 10, 12, 13,000 RPM. So you've got that as the multiplier. Because they can rev there, the airflow through the cylinder head, through the engine, is already optimized for that higher RPM. Because, again, a lot of people would sort of say, well, okay, we've got our automotive engine that revs to 7. No problem, let's just put good components in it and rev it to 12. Problem solved. But the reality for anyone who's run an engine on a dyno, you sort of, if your factory engine redlines at 7,000, you probably find peak power is happening at 64, 6,500, and it's already rolling over and the torque is absolutely falling off a cliff. So simply revving the engine to 12,000 RPM is not going to achieve anything. What you then have to do is redevelop the head, the cams, the valves, etc., so that it will actually be efficient and flow air at that higher RPM. Correct? That all sort of how it works?
Absolutely, yeah. And the more you modify something away from what its sort of original intent was, as you know, the harder and harder it gets, and you end up down these sort of long rabbit holes of re-engineering stuff that you never really wanted to get involved in, but it becomes a byproduct of that. So the beauty to us was with using the motorcycle-based sort of designs, they're really not different to a really modern Formula One racing engine from 20 odd years ago. The architecture, the design is very similar. You're basically getting racing technology for cents on the dollar that a big OEM has already put development into and sell it as a road bike with a warranty. So it's
it's pretty impressive. I often, back when I was running my old tuning shop, and people would say, I've got this car and I want to go from the 200 horsepower it's got now to 600 horsepower. So you sort of look at the options of, we can rebuild the engine to make it strong enough to take turbocharging and then run this turbocharger, and that'll get us to 600 horsepower. Then you've got something, though, that's every element of it is heavily modified. And to a degree, with modifications come reliability problems. As you mentioned there, you've got an OE design component that has a warranty on it. It's designed to do the task. So the other way I always looked at it when a customer had a power target, like, well, would it make more sense to find an engine off the shelf that in production trim makes your target power, and then look at the feasibility of engine swapping? Now, obviously that's not always possible, but I think it's just a different way of looking at getting a solution to that particular problem.
Yeah, that's absolutely right.
All right, so you've got this sort of plan in mind here. When you're looking at your available motorcycle engine combinations, did it immediately sort of narrow down to an obvious contender? Can only imagine there's a fair few options out there.
Yeah, it sort of really came down to two. We had a capacity in mind, which was the 2.4 litres, which we're going to be able to run in the Speedway competitions. So immediately, we just did the simple maths, and that's 1200 cc's. Kawasaki had a really, really good, strong engine in the ZX12R, and the obvious other candidate was really the Hayabusa, the Suzuki engine, which had been around for a while then, was quite well established, and people had power tech at that stage. Maybe Hartley was just getting going. There'd already been a few sort of 8-cylinder V8 developments around that Hayabusa engine, which we took quite close note of.
The Hayabusa, though, again, I'm not a sport bike guy, but they 1500cc out of the box?
They were 1300 back at that point, and they crept them up, I think, to 1380 in the Generation 2.
Oh, maybe I'm thinking RPE, I think, offered a 3-litre variant, but
They do a bigger sports stroke version, yeah.
But again, you would have been, even in base form, 1300 cc's, you're obviously at 2.6 then, so would have required more work to sleeve it or de-stroke it to get it back down to your 2.4.
And then when we looked at the Kawasaki in stock form, it was probably a little bit in a better state of tune than what the Hayabusa engine was. What we liked about it was that the bore centres on the engine were 90 millimetres, which was a couple of millimetres more than what the Hayabusa was. Even though it was a smaller capacity engine, it had a bigger bore, it had bigger inlet valves, bigger exhaust valves, and obviously a corresponding shorter stroke. So it was really a higher performance engine than what the Hayabusa was in stock form. We liked that specifically for what we wanted to do, that that cylinder bore spacing is quite a critical dimension, because that becomes the distance between cylinders, becomes the distance between your main bearings. And when you're designing a new crankshaft or trying to make an 8-cylinder engine using these existing cylinder heads, you've got that key dimension that suddenly you're trying to fit main bearings, crankshaft webs, and then two side-by-side connecting rods into, whereas the original manufacturer just had to fit one connecting rod. So a couple of mils doesn't sound like much, but when you're trying to package that in and get your counterweighting all worked out, every millimetre you're really fighting for. So that did make a big difference.
Okay. Just in terms of that bore versus stroke ratio, is it as simple as the larger the bore, the more over square we are, larger bore, shorter stroke, that just opens the engine up to being more efficient at higher and higher RPM? I mean, you mentioned there you can fit, obviously, with a larger bore, larger valves, which, all other things being equal, can improve airflow. Is it that simple, or is it just very, very complex?
No, it basically is that simple. The bigger the bore stroke ratio, you have bigger valves. You're just going to bias the engine performance up to a higher RPM point. So, what we've found, and it comes back to that BMEP number we talked about, that's reasonably constant between all different families of engine, whether it's gasoline or diesel or turbocharging. They all fall into these sort of pretty tight little groups. Then your torque is really just going to be a function of your engine capacity. One of the things people always say, it's a motorcycle engine, it's got no torque, which isn't really the case. It's got as much torque as a 2.4 litre engine should have, but it's just going to develop that torque at a higher RPM point, because that's where the bore stroke ratio and the valve sizes have made the engine more efficient. But then obviously, because you're making that torque at a higher RPM level, then your power is going to be correspondingly higher in terms of power per litre.
Yep, okay. All right, in terms of complexity of the design, and I have no doubt that there's plenty here, I'm not 100% familiar with the ZX12R. I tuned one of your engines, but so long ago I can't really remember too much about it. I know, having had a fairly close in-depth look at the RPE Hayabusa-based V8, the nice aspect with those engines is that essentially all they needed to develop, I say all like it's a simple task, clearly it's not, I'm not trying to undermine that, but all they needed to develop was a crankshaft and a crankcase, because the factory Hayabusa sleeves, cylinder liners, whatever you want to call them, and heads then could bolt onto that block. Now, again, there's a lot more to it. Does the ZX12R work in a similar way, or did you have to develop a full crankcase including the sleeves?
No, the ZX12 has a separate cylinder block or barrels, sort of whatever you want to call it, same as what the Hayabusa does. So certainly, as for our first generation engine, that was really the easiest way to go. We could take that as part. It was relatively inexpensive because it's made in large volumes. It's already got the nickel plating. We just sort of use that. So what we had to really fundamentally design was the crankcases, the crankshaft, connecting rods, the oiling system, which is always a dry sump integrated oiling system, and then the camshaft drives for the cylinder heads as well.
Yeah, I guess with that you've got the two heads, one obviously turned around 180 degrees versus the other, so you've got a cam chain at both ends of the engine, and you've got to incorporate a drive to the crankshaft for both of those?
Correct, yeah. So we basically use the same cylinder head on both left and right bank. One gets turned around so that both the inlets are in the middle, and then there's some sort of engineering work in the crankshaft to make sure you've got provision for a cam drive at both ends.
Yeah, okay. In terms of the options for making the crankcase, I guess at this stage, if you're looking at a one-off or a very small run, casting would make no sense. So billet would be the winner. Am I right?
Yeah, 100%. Yeah, we've always machined the crankcases from billet. We're sort of using 6061, and haven't really found. I guess our numbers. We're not building hundreds or thousands of engines a year, but I think to be economic for the casting, we'd probably want to be making 100 odd engines a year before the tooling and all of that sort of investment would be worthwhile. Certainly with modern machinery, and if you're doing good batch sizes, cost of machining from solid comes down quite significantly.
Yeah. Interested in diving into the software that you're actually using for the modelling on this project.
Yeah, we've always been into SolidWorks. Yeah, a good tool for us, and we've sort of developed some good proficiency with it, especially working in a sort of group environment collaboratively. So yeah, we've sort of been on SolidWorks from the get-go.
How about aspects such as finite element stress analysis, essentially having the confidence before you machine any of those components that the part is fit for purpose, that your crankcase is going to be rigid enough, that your crankshaft itself, again, is going to be rigid enough?
Yeah, like back in the original days, I guess we sort of didn't know what we didn't know, so we didn't really do a lot of FEA at all. Do more now, but back then, I guess a lot of it a bit more fundamental, just Excel spreadsheets, and we certainly got quite heavily into the analysis side of things, but more with sort of more analytical means rather than the FEA type simulation. So there was that side of it, mostly around the crankshaft, like bearing sizes. Simulating that, you can quite easily calculate the gas loads on the piston, the inertial loads, just from the speed and the accelerations. You'd have an estimate of what your component weights were even before you received them or before you made them. That would all go into big spreadsheets that you can sort of move things around and work out where you were. And then also looking at the counterweighting and your balance factors on the crankshaft was something we put a lot of effort into.
What was, I guess, the most challenging aspect of this project?
Oh, look, it actually all went reasonably well. I don't think there was any like big, oh no moments. The sequence we went through with the very first engine, we just made one to start with. A lot of dyno work. We sort of just got it tuned up and we were sort of running it. And then we'd do 5-10 hours on the dyno, back to the workshop, strip the whole engine down, go right through it, see what we were happy with, what we weren't. The biggest thing at that stage was looking at rod bearings, oiling, lubrication. We needed to sort of move some of our sort of oiling priorities around. I guess probably what we did to start with, we've always picked like an OEM bearing to use. We were never at the point where we'd go to a bearing manufacturer and say, hey, we need a custom bearing for this one-off engine that we're building. So you end up picking something that's close to the sizing you want. At that point, we probably didn't really appreciate that there are bearings and then there are bearings. So the first ones we were getting, they're all like a tri-metal bearing, but the load capacities weren't really what we should have been getting. So then it was a case of, okay, now we're stuck with these bearing sizes. How do we try and find something a bit more durable for what we want to do? So a lot of learning there, but it's all just part of that normal development process.
In terms of what you were mentioning before, the bore spacing and fitting 2 connecting rods on the same journal, as opposed to obviously just one in the conventional 4-cylinder application of the ZX12R. What sort of compromises were there in terms of the width of those connecting rod big end bearings?
Yeah, you're always looking for a fairly narrow bearing. You don't have the luxury of really going for a super wide bearing. Probably the mains are most important, but we were always trying to get a decent overlap in the crankshaft as well for its stability. You're
talking there about an overlap of the main journal versus the rod journals?
Yeah, correct. And we do, I guess, stepping back also to what your previous question was about the FEA. In the absence of that in 15 odd years ago, we would do a lot of benchmarking as well. We'd look at, pour through magazines and technical articles and measurements and just trying to get all those sort of key parameters of every high performance engine that we could really. We've got spreadsheets of main bearing diameters, bore spacings and speeds. So really just trying to get a feel for what sort of ballpark we should be.
What's already been proven is acceptable for a given engine configuration?
Yeah, correct.
I think that actually also bears just diving deeper into. We mentioned FEA, and I think this really comes probably more down to our 3D modelling and CAD as well as our fabrication fundamentals courses, and sort of trying to get out there that, hey, at an entry level, a hobbyist level, enthusiast level, you don't necessarily need to have done a PhD like you have yourself. If you've got at least a basic foundation of engineering principles, what you can do is you're benchmarking, like you say. I mean, we're talking here about maybe the design of a suspension wishbone, for example. How big does it have to be? What size rod end should we be using? Well, we don't necessarily have to design this from the ground up. A casual walk around the pits at any race meeting, you're going to be able to have a look at numerous cars that most often will have been developed by an OEM manufacturer or at least a race car designer. So you can sort of get a bit of a concept of like, oh, okay, well, this car weighs about this. It's kind of the same dimensions of what I'm looking at, and this is the size of rod end they're using on the wishbone. So we're probably, safe to say, if we go that size or maybe step it up one, we're probably at least in the ballpark without actually having to go through a first principles approach to, is this part going to be fit for purpose? It sounds like exactly what you were doing here, really.
Yeah, you can't be too proud to adopt other people's ideas or solutions when they're good ones. And if you're going to be pushing the limits in terms of like making things lighter and smaller or new designs, yeah, you just got to make sure you've got the knowledge, the tools, and the resources to be able to do that. If you don't have those, then yeah, by all means, do your benchmarking and take that as a good guide.
All right. Well, let's get on to the interesting bit. Once this thing hits the dyno, is it as simple as you take the power that a ZX12R makes and double it? I'm guessing there's a bit more going on.
Yeah, look, we were sort of pleasantly surprised with the first running we had on the engine. I think we probably, with a little bit of just development with the fueling and the exhaust systems, I think we were making just slightly more than what twice the ZX12R engine would have been, which in some ways was probably predictable. We only had 5 main bearings instead of multiplying the 4-cylinder by 2. So main bearings per cylinder we had less. We were driving 1 oil pump, not 2. Some of those parasitic losses we had weren't doubled, whereas the power produced by the number of cylinders was doubled. So yeah, the power was very good. The power delivery was excellent. We got it, this particular one, in the midget car. I drove it for 3 or 4 races, I think, as a bit of a shakedown. First to admit I'm sort of no great shakes to driver. I'd sort of hustle around, try and keep out of trouble. But we had a big international series coming up at Western Springs. They do that every year, and we had we had a bit of faith in the potential of our car. We had a good team of guys that were all sort of really into the racing. We had an American guy called Davey Ray organised to come down and drive our new car for us in the international series, which we were super excited about. Car was all ready. He turned up on the first night. I think we qualified on pole for the feature, and we sort of we won the first big race that he did in it in front of this big huge crowd at Western Springs. So
couldn't have gone much better.
Yeah, set our world upside down. Really, we were sort of walking on cloud 9 for a few days after that.
Yeah, I can understand that. We haven't actually talked about power numbers, so let's just dive back into that. What sort of power did it produce, and what RPM range was it sort of running through?
Yeah, we were pretty conservative. We were running up to 11,600 RPM, which is really just the standard red line on the motorcycle. Cylinder heads, springs, cams were all standard, so we knew it was going to be safe running to there. I think we were making something like 370, 380 horsepower at around 10,000 RPM.
Wow. Suffice to say, a substantial step up from the 3SGE.
Yeah, absolutely. Yeah, in the cars, they're a 400 odd kilogram car running methanol, so they're a pretty lively little beast to drive.
Yeah, I can imagine that'd be a lot of fun to drive. So you decided that wasn't enough, and you actually took the car to the US to compete in one of their major events?
Yeah, we had the opportunity to take the car to Australia, actually, just following that to the Australian Championships. Got some support from some local Australians that had sort of seen the car at Western Springs and were really keen to sort of host us and help us out. So we flew the car all the way over to Perth, where they've got a big half-mile track at Kwinana. And we thought, man, we just got to get this thing up on the big track and let her go for gold and see what she can do. And that wasn't a smooth race meeting either. We sort of blew up drive lines and blew up diffs and all sorts of other things as part of that development process. But ended up making the feature halfway through the race. We'd been crashed, we'd been spun out, we were in last place, but ended up coming through on the second to last lap to take the lead and win that Australian Championship as well in that same season. So yeah, that really just set things off going again. Had lots of interest in the engine, lots of people saying, hey, can I get one of these? So that sort of really sort of catapulted us into, let's see if we can turn this thing into a little business.
Okay, so you're looking at it now that you've got a viable product and you've got people lined up to potentially sell them to these people. The old case of win on Sunday, sell on Monday.
Yeah, absolutely. It was sort of true for them. You get a lot of knockers before you start saying, oh, that's not going to work for any one of 10 different reasons. But once you put it on the track and you show them that it runs and it's durable and it's fast, then some of those doubters just tend to drop away.
So is it at this point you've sort of decided to take this as a full-time gig producing these engines, or is there a little bit more to it still?
Yeah, there was still a bit of a sort of part-time sort of hobby, do it when I could at that stage, probably for another year. And then for various reasons, I thought, all right, now's the time. I need to sort of get into my own business and see what I can make of that. So that was in around 2008, I think. And after that, that's when we started into Prototipo, my current business. That's when that was really formed. My current business partner, Nick, who's sort of part owner of Prototipo, half owner as well, he sort of joined me really around then, actually. So it's been going on for a long time.
It's probably a good time to maybe get a sort of a 30,000 foot view of Prototipo as it sits today, sort of location, number of staff, and your services and products offered.
Yeah, cool. Now we're in Auckland, New Zealand. We've got two sites. Our sort of engineering offices, engine build, and sort of engineering work is in Mount Wellington in Auckland. We've got another site out at Ardmore Airport where we do our sort of engine testing. Our dyno is out there, and we do some other business to do with amphibious vehicles, the quad ski, which we were involved in designing and developing out there. All up, we have 12 people and a real range of sort of engineers, technical guys, parts, service, administration. Got a really, really good team. A lot of us have worked together for a long time now. We've got a good mix.
And at this point, how much of the business is involved around the Synergy V8 and the further developments of that, which we'll dive into shortly?
Yeah, we've sort of got multiple aspects. One is the sale of our own engines, which is probably 10 to 20% of our business. We do consulting work, design, development, manufacturing, and some production for other companies in terms of like bespoke engine, low volume products. That's probably another 50% of our business. And then the amphibious vehicle parts, sales, service, development, that would be the remainder.
Okay, I've got to ask, we're going off on a bit of a tangent, but amphibious vehicles, that seems like maybe an odd fit for Prototipo. How does that come about? Are we talking here a performance amphibious vehicle? Is there such a thing?
Yeah, there is actually. A company called Gibbs Amphibians. I was owned by a very successful local businessman, Alan Gibbs, who had a vision for creating a really dual-purpose, well-performing amphibious vehicle. At that point, I was had started Prototipo. We were looking for engineering projects. He knew about the design work we've been doing on engines and with the racing motorcycles and things like that. He came along and said, "Hey, would you like to, help me develop some really sort of high-performing amphibious vehicles?" Which we were involved with him for a long time, really. The main project that we developed and designed was the quad ski, which is really a cross between a four-wheel ATV quad bike and a personal watercraft. So that would do 80 kilometres an hour on land, on road, off road. Quite a capable vehicle. You drive it into the water, press a button, 5 seconds later the wheels have retracted up out of the water. It's also got a water jet incorporated into the vehicle, and it can do 75, 80 kilometres an hour on the water as well. So really sort of a dual purpose type vehicle.
I don't know if I've got a use case for that personally, but it does sound like a hell of a lot of fun.
A hell of a lot of fun, yeah. Great toy. They went into production with those in Detroit, Michigan. So a lot of our team were based up there for a period of time, helping with the design, the development, the durability testing, and about 1,000 were built over a 3-year period.
Okay, interesting.
Yeah, and that used the BMW K1300 motorcycle engine, which we had a contract to buy from BMW, and it needed a reasonably sophisticated transmission bolted on the back of that to separate the drive from the engine to the water jet and the road wheels as well. So that was quite a big project we had involvement in.
Interesting. Let's get back to the V8 and fast forward again to your trip to the Chilli Bowl.
Yeah, in terms of speedway racing, and especially midget racing, which is a particular class of speedway car, open wheel, small car, no wings. The race called the Chilli Bowl is really the holy grail. Happens in Tulsa, Oklahoma, just after Christmas, or early January actually, every year. So middle of the US winter, it's snow for hundreds of miles around there. But because it's in the middle of winter, it's basically off season for every other type of motorsport, and it's an indoor race. The Tulsa Showgrounds, I think, is one of the largest unsupported span buildings in the world. So they actually built this whole speedway track inside the building. All the pits, the big trucks, the big haulers all drive into this building, unpack, everyone sets up. The event takes a week. They typically get between 300 and 350 entries for the main event. There's 4 or 5 nights of qualifying. They break it up into individual groups. Might be some 90 odd cars per group, and they all sort of race through each of the qualifying nights to try and get through into the A main that night. And then the first 2 or 3 out of that A main go into the main feature on the Saturday, which is that's what everyone wants to be. Everyone wants to be in that. If you don't make that, then you have to qualify through the heats again on the Saturday, and you might have 12 races to get through on the Saturday if you want to try and slowly make your way up and make it to the main feature. Because it's off season, they get entries, they get entrants from all different forms of American racing. You'll get IndyCar guys, NASCAR guys, all the sprint car guys, open wheel, the midget guys. It's a real sort of who's who to go there and to make the main event and or even to win the Chilli Bowl. Is just it's a real crowning achievement for a speedway team or for a driver.
I guess the obvious question is how did it pan out for you?
Yeah, it was good actually. We just had this magic week where we took two really sort of top Kiwi drivers, Michael Pickens and Brad Mosen, who were really two of the and still are two of the top midget racing drivers in the country. So two Kiwi drivers. We had two of our Synergy V8 engines, two locally built chassis with Justin Inslee. Took them all up there. Had a really good team of people that went up. Michael drove first on his qualifying night, and after his first heat race, his car looked different. It sounded different. I think he might have left the field in his heat race, and it just sounded awesome. Big queue outside the promoter's office saying, "Hey, you've got to ban these guys. You've got to ban them. You can't let them run." But they were like, "Oh, well, they're here now. We're going to let them run." So Michael ended up qualifying right through to his qualifying A main. He was sick as a dog. He was sort of asleep with the flu 20 minutes before his race. They had a magic race, made the lead, ended up finishing second, qualified straight through to the A main, which was amazing. And then Brad was running on the Wednesday night. Had a lot of pressure on him by that stage with Michael. Michael doing well. Again, just sort of drove like a champ, showed what the car could do. He qualified third in his A main, so he also qualified straight through into the Saturday night final. So that sort of set the whole place alight, really. There's a whole lot of these big established American teams. They turn up with big haulers, 5 identical cars all lined up. And by the end of Friday night, they don't have any cars in the A main. And we're these sort of Kiwi guys with 2 cars come from the middle of nowhere. We've got them all coming out of the back of a budget rental truck. And suddenly 2 cars in the top 10 qualifying into the A main. So
at this time, what was the alternate, or traditional, I should say, engine of choice for a midget?
At that point, there would have been there was a bunch of Mopar engines, custom sort of block with typically like the NASCAR V8, one of their cylinder heads. The Slinger was always strong. That was nominally a Ford Pinto based, so overhead cam engine, but not resembling a Ford Pinto really in any shape or form. That was a high RPM, very powerful engine. There was the Pink Fords. They were always very well developed, very, very well thought out engine. And I think maybe the TRD, that maybe the Toyotas were just starting to sort of come into the play then as well.
And could you give us a sense of how far ahead of the game the Synergy V8 was power-wise?
I think we actually detuned the engines quite a lot for that event because it's quite a small indoor track. The last thing we needed was sort of 380 horsepower, so we ended up doing a bit of work with camshafts. We were deliberately just trying to make the engine probably half as powerful at 10,000 RPM and twice as powerful at 3,000 RPM and making it super easy to drive and linear. And that worked pretty well for us.
So just a nice wide power band instead of it being peaky.
Absolutely. Just make it not falling into the trap of looking at what's the high number. It's just making it sort of easy for the driver to make the use out of what he's got.
I think it's very easy to get all hung up on that peak number, but it's just so important to look at the area under the curve and how that's going to translate into the drivability of the car, and particularly if you've got something that's a road race car that's very, very peaky, how that works when you're changing gears and maybe falling out of that power band as well. Anyway, back to your situation. So fast forward to the end of this story. How did you fare with your 2 drivers?
Oh, I think at one point we might have even been in like second or third. We were just like hanging on to our seats halfway through, and then I think Brad had an accident. Michael maybe got spun around. Just the normal racing stuff happened. I think we might have ended up like 7th and 11th. But certainly the track up there is a very strange beast to set your car up for, that we probably didn't have the traction at the end of the race that we would have liked. But hey, both cars finished. We were super, super happy with making it to that event and how well the cars went in the event.
So essentially the concept was proven. And before we started recording this, you mentioned that the unlimited rulebook for these cars may have been changed in light of your success.
Yeah, something we've struck on occasion, and that when you're a little bit different to everyone else, and you show that hey, you're competitive. When we tried to enter to go back the next year, the sort of run what you brung event suddenly had a few little rules pop up, and we weren't as welcome that second year as we were the first year. So no, we couldn't go there anymore.
Okay. That's a shame. But you have found other uses for the Synergy V8. One of the ones that has always interested me, and this is kind of how I met you, was tuning a local Toyota GT86 endurance race car that had been set up with one of your, I think it was a 3-litre variant of your Synergy V8 and backed by a Hollinger paddle-shifted transmission. And you actually offer, maybe not the Hollinger transmission side of things, but you actually offer a kind of like, I call it a plug and play package for the GT86, which always on face value for me kind of seemed like an unusual choice, given obviously this is a substantially expensive engine package by the time we consider, all of the ancillary items, the electronics and the transmission in a car that's now secondhand relatively cheap. What was the impetus behind that choice?
Yeah, I think in hindsight, we would definitely agree with you on that. We sort of liked it because at the point that we started doing that, the 86 or the BRZ was like a brand new car out on the market. It was quite hot. It was quite exciting. There was some aftermarket support developing for it, but the engine was really not much chop in the standard car.
Can confirm.
Yeah. So we thought, hey, if you can get rid of the 200 odd horsepower 4-cylinder, put in a 400 horsepower 8-cylinder engine, that's going to be a pretty cool car. And I think we like the challenge of doing the conversion, and we set ourselves a pretty high standard where we wanted to be able to open the bonnet and have it just look like a real OEM, as if TRD or Toyota had offered that engine and try and make it look very polished. So we put a lot of work into that presentation, the tuning, and it really was plug and play. You could literally in a weekend unbolt the FA20, the kit that we put together. It used the same engine mounts, same. You didn't have to drill a single hole. Use all the same fastener pickups for coolant pumps, and all the plumbing was supplied. The dry sump tank had a nice custom tank that fit up in the fender. Everything was done. Made a great car. We sort of certainly enjoyed having our test car and developing that. Really, obviously, transformed the car from a pretty medium level performance car into something that was quite special. But the cost of the conversion kit was multiples of what the base car cost to buy. So we were always going to have very limited sort of clientele that would really want to have a car like that. And I think we built sort of half a dozen odd kits that went to different places around the world. But the economics were difficult in that if you had someone with a multi-$100,000 car, they'd have no problem spending similar amounts on their car because it's fractions. But for a $20,000 car, you're not going to spend the extra.
Yeah, okay. Well, that was kind of where I saw it going. So obviously, I didn't quite miss the mark on that one. One of the more high-profile applications of that, I think, probably it's fair to say, was that Jun have your engine running in one of their cars over in Japan.
Yes, that's right. Yeah, they were one of the original sort of customers who wanted to use that as a promotional tool, for their business as well, which was great. They're great to work with.
I just wanted to take a moment out of our interview with Simon here and talk about a package of courses that we've put together that I know you're going to love if you're enjoying this chat, and that is our engine building starter package. And I know for a lot of enthusiasts, they think that building their own engines is not something that they're going to be able to take on, but the reality is nothing could be further from the truth. With the right tools, enough patience, and a little bit of dedication, any home enthusiast is capable of building quality and reliable performance engines. This package includes everything you need to know. It starts with our Engine Building Fundamentals course, which, as its name implies, teaches you the fundamentals of engine building and the skills required. You will learn about the clearances and tolerances inside the engine. You'll also learn about the common machining operations that we need to perform when we're getting an engine ready for assembly. This is important because it will allow you to speak the same language as your engine machinist. Moving on from here, we move into our practical engine building course, and this builds on the knowledge taught in our fundamentals course, and this time we present a 10-step process that you can apply to building your own engine irrespective what type of engine it is. It's important to mention all of these courses are generic. So whether you're building a simple pushrod V8, maybe a quad cam V12, whether it's turbocharged, naturally aspirated or supercharged, this course package will be perfect for you. We've broken the engine building process down into a 10-step process because this way each of those individual steps is relatively quick and easy to complete, and in no time you've got a completely assembled engine. You're going to have the confidence that the parts you've chosen are correct for the application, all of the clearances are suitable for your use, and you're going to know that when it comes time to start that engine for the first time, it's going to start and run, delivering great power, great torque, and most importantly, great reliability. The second part of this course includes a library of worked examples, which is where we go through a real-time breakdown of building a particular engine. Here, we vary the type of engine we're working on so that you're going to get experience on a wide range of different platforms. This package also includes our How to Degree a Cam course, and this is one of the most common upgrades made when building a performance engine. Getting the right cam and degreeing it correctly can make a massive difference to the performance of your engine, but if you don't degree it correctly or dial it in correctly to the manufacturer's recommendations, you could be losing out on potential power, or more importantly, you could end up damaging your engine with piston to valve or valve to valve contact. This course goes through the process of degreeing a cam, and again, it's generic. It doesn't matter whether you're dealing with a pushrod engine or a double overhead cam or maybe even a quad cam engine. The process is exactly the same. We've broken degreeing a cam down into the HPA 6-step process, and as usual, we've got a library of worked examples you can watch to expand your knowledge on a wider range of different engine types. On top of this, you're going to get 24 years of gold membership, which gives you access to our weekly live webinars, our archive with over 350 hours of existing webinar content, and you'll get access to our private members only forum. This package usually sells for $299 US. You can use the coupon code Synergy50 and that'll get you $50 off your purchase. Remember, even using this discount code, you're still protected with our 60-day no questions asked money back guarantee. So there's absolutely no downsides giving these courses a test drive. We'll put that coupon code in the show notes so it's super easy for you to find. Let's get back to our interview now. Now, I want to come back to the engine of yours that I tuned locally, and this is an Instagram post that we've put up, and it always gets some very heated conversation. Quite a specific topic, but this is the inlet trumpet. So more specifically, these engines, as with most sport motorcycles, run individual throttle bodies. The interesting part here is that the inlet trumpets, and this is in this photo that we post, are different lengths from cylinder sort of front cylinders through to the rear cylinders. And if we look at tuning options for individual throttle bodies, the trumpet length is quite an important one, and we can influence the sort of tuning element of the airflow into the cylinders by length of this trumpet. However, when they're different, obviously we're optimizing then the airflow into different cylinders at different points. As I understand it, remembering to the chat we had about this back at the time, which is a number of years ago now, these trumpets were production trumpets, is that correct?
No, they were a specially made trumpet that we...
Maybe the point I'm more going with is that this technique of different trumpet lengths is also used by OEs?
Yeah, it is actually quite often. Yeah, most of the sports bikes would have different trumpet lengths for inner or outer cylinders. I mean, I can certainly understand how that photo would probably wind some of the purists up, but for us, for that particular application, was predominantly about packaging. Like, we really wanted as long a trumpet as we could fit into that car to get our torque peak where we wanted it. But the bottom line's quite low in the 86, so we physically couldn't fit as long a trumpet as we wanted in the front. But in saying that, what we've really come to doing with our Speedway engines was having different length trumpets deliberately on different cylinders. Because again, if you're looking at peak numbers, you probably want all the trumpets the same length, all tuning at just the right RPM, and you're going to get a nice peak at that 1 RPM and save with your power. But by the same token, when all the cylinders are in tune, 1500 RPM later, they're all going to be out of tune, and you're going to see the peaks in your torque curve, peaks and troughs. So what we tried to do is basically shift the half the peaks around. We'd work out what the wavelength was. Half the trumpets would be half a wavelength out of tune compared to the others. And then when you look at the torque curve, suddenly instead of having peaks and troughs, you've got this very nice flat curve, which for a Speedway application where you're really high power to weight, you're very traction limited, and you want the driver to have a really sensitive feel of, okay, I want 5% more torque, so I'm going to put my foot down by 5% and deliver what he wants. Then having that smooth torque curve was important. We took the same philosophy for some of the other applications. Even though we were package constrained, they certainly helped the torque curve.
Okay. So there's two follow-on questions that this brings up for me, and I'm asking this as someone uninvolved, although clearly I was. When you've got this discrepancy in the trumpet length, that's going to have an effect, therefore, on the volumetric efficiency of these cylinders with short versus long trumpets. Essentially, the cylinder fill is not going to be the same. Yet when we're tuning from a collector-based lambda sensor, we're kind of getting the average of all of the four cylinders that are feeding that particular collector. So in essence, what I'm saying here is with those different trumpet lengths, we're likely to have two cylinders maybe a little rich, maybe two cylinders a little lean. We're going to get our overall lambda sort of where we want it to be. The only real way of individually tuning these would be to use individual cylinder lambda sensors. This is one of the questions that comes up when we post this. Why doesn't the engine essentially instantly fall to pieces because of the tuning issue this creates? Obviously, it's not that big of an issue.
It's not that big of an issue. And to be honest, with those cars, we just use collector lambda. We'd set the target lambda somewhere in the middle of the range where we knew if we were a little bit rich or a little bit lean, or from that range, you're on a very shallow part of the curve, and the engine's going to be really happy wherever it ends up. Saying in mind, we're naturally aspirated, we're on gasoline, we're pretty safe if we were.
The tuning envelope is a little bit wider than if it was a very highly strung turbocharged engine.
100%, yeah. And later on, we've put individual cylinder lambdas in, and we would have done individual cylinder maps, but obviously the tuning demand to do that is quite a lot higher. You will see a slight improvement from doing it, but it's not hugely significant.
Okay. And that second follow-on question, just in terms of if we've got at a given RPM range some cylinders effectively with higher cylinder pressure than others, does this have any negative impacts in terms of harmonics on the engine?
Not that we could determine. And it is probably worth noting as well that although you might have an 8-cylinder engine with 8 identical camshafts and identical ports, very rarely are you going to get 8 cylinders all operating completely the same. When you start putting in-cylinder pressure instrumentation or actually putting individual cylinder lambdas on an engine where nominally everything's meant to be the same, it's quite eye-opening how different individual cylinders work. And partly that is the exhaust dynamics. You'll have different pulses coming back at different times. So the notion that every cylinder works exactly the same, even in an engine where nominally they should, that's not really a thing.
Yeah, I think that just comes again from those who are maybe fresh to the tuning scene, assuming that would be the case. One of our 86 development cars, which still had the FA20, albeit turbocharged, I had the benefit of individual cylinder lambda as well as individual cylinder EGT. And I can't remember specifically, I did do individual cylinder fuel tuning on that to equalize the lambda. And I think it was something like 3,500 RPM. And there is a funny sort of hole in the torque curve in that FA20 anyway. One cylinder, I forget which one it was now, maybe number 3, that needed about a 10% trim over a 500 to 800 RPM range to get it back in line with the others. Higher in the rev range, everything was probably within about sort of 3 to 5%. But I mean, even that 3 to 5%, most people would, on face value, expect that to be zero. But it's not. They are different. So, I think that's an important point to make. It's not obviously an issue with your engines. All right, let's move on, because when you were in the workshop with me and I was tuning that engine, we had a bit of a chat about some of your upcoming developments, which again, we're talking 8 years ago now, so a lot of this is now sort of relatively old for you. But what were your developments beyond that original, I guess, Gen 1 Synergy engine?
Yeah, like that sort of, we've learned a lot from the Gen 1 engine, and we've built a number of them, and had some really good successes in different forms of motorsport, but that really was our first go. And like anything, we didn't know what we didn't know. We were fairly naive at that stage, and always had the idea that we could do things better if we had a second go. Had the opportunity to work with local guy Reg Cook, who's very sort of well known in motorsport in New Zealand. He really had some high ambitions about land speed record racing, and he started talking to us about collaborating on a 2-litre normally aspirated land speed record attempt. So we sort of did some numbers, and we thought, okay, let's follow the same formula again. We want to go more cylinders. We want 8 cylinders, not 4. How would a 2-litre V8 look? What would the cylinder head sort of components look like? What would the bottom end look like? that really came around to, at that point, the BMW S1000RR sort of superbike, 1000cc sport bike was really the pick of the bunch. Again, it had bigger bore centers, it had bigger bore, it had bigger valves. It was really just a race bike, sort of packaged up for the road. So we really kicked off again with everything we'd learned from the first one and designed a new 2-litre V8 around that BMW cylinder head. So that took place over a sort of 18-month, 2-year period. A lot of dyno work, got them into Regis cars. One was a production coupe, the Nissan NX coupe he'd campaigned with different engines in it. And then he also had a big Wairua, big streamliner that we put the 2-litre V8 engine into as well. And then we took those to Bonneville, I think, 2017, and set a bunch of land speed records in a whole bunch of different classes with those engines.
Okay. Let's just come back again a couple of steps, and we'll talk a little bit about the BMW cylinder head or engine in general, but really it's the cylinder head that's the key aspect here. The rest of the engine's just there to basically contain everything that the head can flow. So that's the part that's really, for the most part, fundamental in making power. What were the steps forward that BMW had made over the original Kawasaki ZX12R? I mean, obviously we've gone from 1200 cc's down to 1000 cc's, but as I understand it, again, I'm not a sport bike guy, but this 1000cc sport bike market, as I understand, is quite hotly contested between the different manufacturers. There's a lot of drive to sort of be the best and the fastest.
Yeah, it is, and the Japanese makers have really had the market to themselves up until that sort of 2009, 2010, when BMW entered with their 1000cc. And BMW really came in with a statement that the Japanese had sort of consolidated around a sort of a similar bore size of 76 to 77 millimeters. They were all fairly conventional. They'd gone to titanium valves, but still with a bucket type follower and the sort of the limitations that gives you with weight and accelerations. BMW came in, they're like, all right, we're just going to go for gold. They went to a bigger bore spacing. They had an 80 millimeter bore. They went straight to DLC coated finger follower valve train titanium valves. They could run the engine to 14,300 RPM, which was 1,000 RPM more than what the Japanese would do. So all of a sudden, the competitors were 160, 170 horsepower. Suddenly BMW was coming out with a 195, 200 horsepower sport bike. It was really quite a special engine.
Wow. Just speaking for a moment to the Japanese manufacturers, do you think this is a case of, sort of, when I say complacency, laziness, that there wasn't a need to develop further because they'd all focused or kind of come down to the same concept of how the engine was developed?
Yeah, I think it was, and they were sort of really happy with that incremental improvement year after year, and they were all quite well matched with each other. And probably the market wasn't demanding anything more at that stage. But BMW, I guess they were the new entrant. They had to be different in order to make an impression. So yeah, they did that.
As a non-sport bike rider, I'm really struggling to see why anyone needs 195 horsepower on a motorcycle. But there's obviously those out there who would be always begging for more. One of the aspects you mentioned there is the valve train arrangement, finger follower versus bucket. As I understand, one of the problems with the bucket is that the diameter of the bucket is kind of going to drive the cam profile that you can use. Is weight, because you mentioned that, is weight another aspect where the finger follower beats the bucket style follower?
Yeah, you really hit on both the important things, like what you want to do with a high RPM engine to make power is obviously lift the valves a long way, and you want to lift them like fast and close them fast. You don't want these big long valve events, otherwise you've got to have compromises sort of lower down on the power curve. So basically the finger follower, it weighs less than what the bucket does, but one end is fixed to the cylinder head, so it's basically just rotating. There's no sort of translation of it, and it's only the thin end on the end of the valve which is moving up and down. So the actual reciprocating weight is about a third of what the bucket is. So you end up with a very, very lightweight sort of valve reciprocating mass.
Again, as I understand it, this is the same technology that F1 engines sort of all gravitated towards?
Absolutely. Like in any performance engine now is going to be a DLC coated finger follower. And we're obviously on coil springs, whereas Formula One are on pneumatic springs. It's not something we're.
That was going to be my next question. Formula One run a pneumatic valve spring, and as I understand it, sort of, I don't know if I've got it quite right, maybe around about the sort of 17,000, 18,000 RPM mark is about the point where a steel spring is essentially not able to keep up. Is that sort of sound about right?
Yeah, maybe not even that much. Probably beyond sort of 16,000 RPM, you'd be. It's just it's like the diminishing returns. You need a stronger spring to be able to return the valve, but then the stronger spring is going to be thicker wire, so it's heavier. So then it's got to return its own mass as well, so it needs to be even stronger. So you end up falling off the end of this
this exponential kind of curve of everything getting really ugly. Obviously, for a pneumatic valve spring, though, that's really not something that's a consumer-based product. There's a lot of practicalities involved in how to pressurize the system and actually get the engine to start. So not really a consumer option, is it?
No, it's certainly not on our radar in the near term.
Okay. Any other technologies associated with this BMW cylinder head?
Apart from the finger follower valve train, the rest of it is just a very well executed, very high flowing, high performing cylinder head. Obviously, titanium valves like is sort of the standard operating practice now. But when you look at the shape of the ports, the combustion chambers, just very, very well done. The head, although it's a smaller engine, it certainly has better port flow than what the Kawasaki 1200cc head does or did.
Okay. Technologies like continuously variable cam control or variable lift, are these not really useful or relevant when we're talking about engines that are revving to 14,500 RPM? And I'm assuming in actual use, when you want maximum power out of them, are operating over a very narrow RPM range?
Yeah, that's right. I mean, if you've got a narrowly focused engine like for a racing application or a hill climb, typically the VVT isn't going to give you enough of a benefit to warrant the complication and the extra cost of and weight of putting it on. In saying that, a lot of the bikes these days and so most modern engines are migrating towards that because, as well as the big power numbers, the competitiveness, people also want to drive them to the dairy, go get the milk. They have to be emissions compliant, which is a huge thing about the idle stability and the low speed, low load combustion stability, because that's primarily that's where the emission cycle is looking at the engine performance. So you will get these two-stage cams or variable sort of geometry valve trains in order to meet both of those objectives.
But again, really for a race application like what you're talking about, it's just not relevant. Added complexity for no real benefit.
Yeah, that's what we've found for sure.
Okay. Another thing I'm interested in here is direct injection as it applies to the sports bike market. And again, I'm clearly not up to speed with these. Is this something that has come in? Are they using it? If not, why not? Obviously, it's become the norm now in passenger vehicles.
Yeah, it isn't something that's come into the sports bikes. May well do in the future. I think one of the prime limitations at the moment is just the high. It would need to be a small injector because the engines are smaller, the bore size, the access for injector, but also high engine speeds. The time to inject quite a significant amount of fuel is very small. So I don't think the availability of the injectors and the controllers for that particular spot is there yet.
Yeah, that makes sense. I mean, if we look at a port injector, while I wouldn't recommend it, we can essentially run those at 100% duty cycle where it's just spraying the entire engine cycle, and obviously a large portion of that's going to end up sitting behind a closed intake valve where it's vaporized by the heat. Whereas a direct injection, you've really only sort of got 25-30% of the engine cycle available to realistically get the fuel in. So yeah, that really creates problems for the injector size and the pressure that we need to run to achieve that. Coming back to the 2-litre based V8, any other complexities, problems or issues that arose during the development of that?
No, look, we had a very smooth run with it before Bonneville. Did a bunch of dyno testing. We did some sort of Bonneville simulations on the dyno, which was really quite nerve-wracking, where we knew the run was going to be a couple of minutes long. So full power, we knew we're going to be using 11 to 14,000 RPM. We're going to do 6 gear changes. So it's just trying to replicate that on the dyno, and the thing's scraping away, and the whole exhaust system's glowing red hot. But sort of do that a few times and then pull everything apart and make sure it's happy. And that side of it was very good. Had certainly no issues with Bonneville. and the engine looked great afterwards. So that was a really good sort of initial outing for the engine. We've learned some more things, and as you sort of do more, and as we found more in engineering and more in any of this development stuff, as soon as you test in a new situation or a new application, you don't need to change too much, and you very well may sort of shake out these little issues that you need to resolve. So the most areas we've mostly been attending to have been the cam chain stability. We've sort of learned a little bit about what happens during these sort of sequential paddle shift gearbox changes, where you can have quite an abrupt change on speeds, and that can do really horrible things to the way the cam chain wants to run in its guides and on the sprockets. So we've had occasions where some of the early engines would jump a cam tooth if they had the wrong situation during a gear change. All easy stuff once you figure out what the problem is to then get to the root of it and implement a fix. But quite often some of these problems, trying to determine the root cause in amongst of other clues can be quite difficult. But no, we're quite happy with where we've got that engine to now.
And what sort of power did it end up producing?
Once we developed them a little bit, the original ones were all standard, and they were sort of making that 400 odd horsepower mark using the OEM cams, very, very minor preparation of cylinder heads, so 200 horsepower per litre. Once we started to develop them a bit more with some like superbike style cams, a lot more lift, duration, we were sort of seeing about that 430, 440 horsepower.
That's absolutely no joke, and I imagine the power density with the weight of that engine would be pretty impressive as well.
Yeah, I mean, at the long block, I think on that one, it's 73 kilograms. So you literally, if you've had your breakfast, you pick it up and carry it around. I think fully assembled, with flywheel and alternator and starter, it's 96 kilograms. So it's a pretty power dense little unit.
Coming back to Bonneville, and particularly those test runs that you were just talking about on the dyno, typically we might do a ramp run on a traditional motorsport based engine, and it might be sort of, let's say, 2 to 8,000 RPM over, 10 seconds, for example. 2 minutes is pretty scary. Is there anything different you are doing with tuning for land speed record racing to keep the engines alive, or are you treating it essentially like a road race engine where you're just optimizing for peak power everywhere?
Look, in terms of tuning, because we're still normally aspirated, we're not turbocharged, we're not really, this type of engine, we're not on the knock threshold. You can really tune it for your optimum lambda, optimum advance, and just go for it. On the engine build side, we would be probably more specific about some of the build settings we would use. Things like your piston ring gaps, for example, we would definitely go for a slightly larger gap, because we know that the amount of heat going into the top ring over a sustained 2-minute period is going to be more than a short pull down a straightaway.
Does that sort of follow on to piston to cylinder wall clearances as well? You run those a little bit looser for the same reason?
Absolutely. Yeah, we'd just be more mindful of that stuff, and then the engine's going to tell you what it wants. You do the runs on the dyno, pull it all down, have a good look, and then just tweak those sort of those clearances from there.
Going a little deeper as well, and just to the engine aspects for land speed record racing, and the exhaust valves obviously have to dissipate a lot of heat, and they primarily do that when they're closed and they contact the seat. As I understand it, I don't machine engines, but you can influence how well that heat transfer works by making that seat width wider. Is that something you play with, or is that really not a consideration?
Not for that particular engine. We haven't found we needed to do that. Again, normally aspirated in more recent projects where we've done a lot more with turbocharging, and again, turbocharged engines that need to run at like sustained high power. We've sort of been doing some durability work on our dyno. We've set it up where we can do some pseudo lap simulations, just running around for 20 minutes or until the vehicle would simulated needed to come in for a tank of fuel anyway. And certainly doing that sustained high power running compared to ramp runs, we've learned a lot about the effects that sort of build up of thermal energy can cause. So in that particular case, especially when you're starting with a motorcycle style cylinder head, which may not have originally been designed for turbocharging, then there's quite a lot of attention that we've needed to pay to exhaust valve materials, right through the details, exhaust guide materials, valve to guide clearance, the seat materials, and like you say, that seat width is quite important as well.
Okay. Just with the different variations of these engines that you've built in terms of capacity, obviously here we're talking about the 2-litre V8, but as I understand it, you've got a 2.4 litre naturally aspirated version, you've got a 2.3 litre forced induction version.
Yeah, that's one. That one's just in build at the moment. We're sort of a project on the go for that one, which will be sort of for Pikes Peak next year.
Amazing.
Which we are really excited about. It'll be 2.3 litres, twin turbocharged, using a lot of the stuff that we've learned more recently from the other turbocharged engines, but applying it to the sort of really high RPM, lightweight, sort of high power density engine.
And can we ask what sort of power you're expecting from that combination?
We're not going too crazy. I think it'll be sort of 800 horsepower. Again, it's drivability. We could easily make big numbers from it, but for the hill climb, you've got to accelerate from 5,000-6,000 RPM up to your 13,000 RPM. So it'll be just trying to make a nice boost number that we can maintain the boost up the mountain and be fairly consistent up the hill.
No, that all makes sense. This sort of leads me to my next question, which is around the changes you're making when you increase the capacity. Obviously, with the 2 litre, really easy to keep the same sort of aspects of bore and stroke as the stock engine. I'm guessing, again, when you're sort of limited with the production cylinder head here, if you want to increase the capacity, you may not have a huge potential to do so with an increase in bore, which will lead you to increasing the stroke. This sort of feeds into the rod-to-stroke ratio. And again, anytime that comes up in conversation, that there's a lot of debate about the pros and cons and the importance, if you will, of rod to stroke ratio. So on that basis, can you give us a quick overview of what rod to stroke ratio means? And from your perspective, is it important? Is it unimportant? And how do you factor that in when you are making a increase in capacity?
Yeah, I think it is important. I don't think we place an undue importance on it because there's a bunch of competing parameters which have all got their own sort of degree of influence. Typically, we would always end up at a fairly high rod-to-stroke ratio, generally 1.9 to 2.2 to 1, which compared to a normal sort of auto engine is probably on the long stroke range anyway. We do like that. You find that secondary acceleration of the piston is reduced with a longer R over L ratio. So your loading on the piston at high engine speeds is a bit less. What quite often drives it for us is that always being length constrained, and we do have a philosophy where we like to keep the crankshaft nicely counterweighted in between each main bearing so that any out of balance forces are contained, and we're not trying to spread out of balance forces across main bearings and have a whole crank that wants to sort of whip its way around, especially in a flat plane arrangement where it's like a 4-cylinder crank. You've got your middle 2 pins are on the same plane as your end 2. If we're length constrained, then quite often the key element of the crankshaft design and getting the right counterweight is your counterweight diameter. But of course, as your counterweight diameter goes further out, you've got to be making sure you've got good clearance to your piston at bottom dead center. So that combination then quite often drives the rod length. So in some cases, we might want a slightly shorter rod length, but for other factors, we tend towards keeping it slightly longer to keep the dynamics of the engine a little bit more stable.
So essentially, unsurprisingly, like any engineering project that's complicated, this is just a series of compromises, and there is no perfect answer in terms of what the bore, the stroke, and hence the rod to stroke ratio is going to be.
Yeah, sure. You throw it all in the mix. You try and decide the right balance of compromises based on your application and what you're trying to do with it. And knowing that, hey, there's no right answer for every situation too. You might pick this number, it might hurt you in one place, but it might help you in another place. So you just tolerate the best mix of what you can do and then develop from there.
Okay. Just before we move on to our next topic, is there sort of anything else you've got that's exciting on the horizon for development around these motorcycle-based V8 engines?
Yeah, we've sort of taken a little bit of a left field, and we've actually got a little 4-cylinder engine that we're just about to start machining on at the moment. Design's all done. It's trying to marry a little bit about what we've learned with the high RPM engines, the turbocharged engines, but bringing it back to a pretty compact, lightweight, and a bit more cost-effective as well. The downside with the 8-cylinder engines is you've got lots of parts. You've got 32 valves. You've got cylinder heads. You've got a lot of expensive parts that we're machining. We sort of want to get some of those benefits of the high RPM and the turbocharging, but come back to a little bit more sort of cost-effective platform. So it's going to be just under 1.8 litres, still run to a little bit over 10,000 RPM, but be fairly highly boosted. So a good power number and super light and compact. And we're hoping that sees a little bit of buy-in in things like rally, circuit race, club race, where some of the traditional engines that we probably cut our teeth on, like your 3 SGEs, your 4G63s, your SR20s, your 4AGEs. They're all quite old engines now, hard to get hold of. They're getting quite rare, and the new breed of engines maybe aren't quite so amenable to your tuning, to your retrofitting, to your turning into club cars.
So you've seen a bit of a gap there.
Yeah, we're just going to see how the little four-cylinder. We've got a couple of applications for it already. It's a little rally car. We're going to put one in. There's our own development car that's going to have one, and just see how that goes with us.
Okay. Moving forward, again, just chatting with you before we started recording here, you're involved with development around the use of hydrogen fuels. And this is sort of alternative fuels, EVs. Obviously, it's been a very hot topic for a few years now. And as I'm sort of seeing it, I mean, it's obviously a constant evolving situation, but as I'm sort of seeing it, some of the big players in the OE market who had sort of touted that by 2030, for example, they were going to be no internal combustion engines, full EV, and we're starting to see a little bit of a pullback on that. There's some infrastructure challenges that come along with mass adoption of EV as well. Hydrogen fuel, and I'm far from an expert on this, but as I see it, has sort of been on the sidelines for a hell of a long time now, and on face value it looks like an ideal alternative to a full EV world, given that it's compatible with our existing internal combustion engine technology. Obviously there's decades of development have gone into those. Give us the sort of the keynotes here on pros and cons of hydrogen and why we haven't seen more mass adoption.
Yeah, look, it's something we've been interested in for a while, and as I said, engineering business and into engines, like you see what's coming up for normal, fossil fuels, and it's only going to get sort of harder and harder. So we sort of want to be knowledgeable and involved in whatever the next wave is. Yeah, like you say, like running an engine on hydrogen, it's not technically that difficult. We had a little S1000R engine, our four-cylinder dyno test engine, that we had a need to do some running on that at hydrogen, and with relatively straightforward sort of looking at the fuel properties and some injector characteristics and a bit of working on the Motec M1 package, we had that running very happily on hydrogen on the dyno and getting some good performance data from that.
I'll stop you there, and just because I haven't had the opportunity to delve into hydrogen at all, how does it compare as a fuel to a normal pump gasoline?
Yeah, look, it's interesting. It's relatively high octane, so very knock resistant, but it's got a very low ignition energy. So you don't need a lot to light it. So you don't need a high energy ignition system. Your normal spark plugs will do it. Downside is that makes it quite prone to pre-ignition as well. So you do have to be careful about heat range spark plugs and hot exhaust valves and anything sort of hot in the chamber. It's obviously very low density, as everyone knows, which means if you're injecting the fuel into the port, you're going to be displacing a lot of air out of the port as the fuel goes in. So typically your volumetric efficiency of the engine is going to be 30 to 40% less than what. So for a given engine, it's going to be less powerful on hydrogen. But in that case, it burns very quickly. So you need less ignition advance. So you get quite efficient, short combustion. So if you are direct injected, you're getting away from that port injection problem. If you're turbocharged, you're getting away from the volumetric efficiency problem. So probably the most efficient, powerful engines are going to be DI turbo, which, as luck would have it, is pretty much the way that everything is going now as well. So that side of it's good. And you can make an engine run very efficiently. And it'll actually, the interesting thing is it'll also run at very lean air-fuel ratios quite happily. And I think that's to do with the very low ignition energy required to burn it. Lambdas of 2, 3.
Oh, wow.
Yeah, and it's just happy as, and you do that, and then the efficiency is sort of getting better and better, and it's just loves it.
Interesting. Yeah, I mean, if you look at that with a conventional pump fuel gasoline, once you sort of get leaner than about 1.05, maybe 1.1 lambda, you sort of get to a point where you can't reliably light off the charge and you start getting random sort of ignition misfire. So that kind of becomes the limit on the lean side of Stoic, albeit that there's an influence on emissions depending on the air fuel ratio or lambda number that you choose as well. So that needs to be taken into consideration.
Yeah, that's quite eye-opening for us, and it seems like it. I mean, burning hydrogen in the engine, it's not the magic bullet. There's no hydrocarbons, so you're not getting any CO2 or carbon monoxide emissions. But you've still got the nitrogen in the air that's going in, and nitrogen, oxygen, high temperature, high pressure. It's going to form the various oxides of nitrogen, which are still a pollutant and a smog-producing gas. But by running quite lean of stoic, you're 2 to 1, 2.5, 3 to 1, the pressure and temperatures are less, and that the formation of the oxides of nitrogen almost becomes insignificant. So it really sort of becomes not an issue at all. We've sort of looked at doing some fuel cell hydrogen projects as well, which is really a step away from the combustion engine, but it's a way of converting the hydrogen gas directly into electricity, and then you'd have a typical electric motor on wheels. And that's another great technology as well. It's maybe not quite as simple as putting it into an IC engine and burning it. The fuel cells, they are expensive, they're not that well available, and they've got their own issues with sort of longevity and contamination of the stack itself. But I guess where our thinking's got to with hydrogen is that there is still a big infrastructure problem with hydrogen, no different to sort of EV chargers. The difference is for everyone's daily driver car, just about everyone has electricity at home. You can take your car home, plug it in, and you're going to leave the house with a full charge. With hydrogen, we're back to having centralized fueling stations, with high pressure tanks, and there aren't a huge amount of those around now, and it's not going to be 1 to 5 years for that infrastructure to come along.
So essentially that infrastructure is going to have to catch up. So we have hydrogen refueling stations everywhere we need them for the knock-on effect to be a viable technology for passenger cars.
For your commuter transport, sure, but our feeling probably is that the horse has already bolted in favour of a battery electric vehicle for that commuter application, just because the infrastructure's it's already there, and the round trip efficiency, you're generating electricity somewhere, hopefully renewably. In New Zealand, we're lucky that's mostly the case. Comes down the power lines into your car, very little losses. It's very efficient transfer of energy. Hydrogen, we still do have the problem where to create the hydrogen sustainably, renewably, it's not a super efficient process. We're losing 40 or more % of the energy in creating the hydrogen, and then to convert it back into useful energy, whether it's mechanical energy from an engine or electrical energy from a fuel cell, we might lose half of that again. So the round trip is not great. But in saying that, there are some applications where it seems like the battery electric technology and the projected where the technology is going to end up in 5 years, still not quite there. Like your big marine applications, your even leisure, marine, boating, heavy transport, the battery just gets so heavy, then the recharging time becomes very long. Your expensive vehicle, your vessel's off the road while it's charging, it's not earning you money. In those cases, hydrogen certainly looks pretty good in that the hydrogen would be a lot lighter than the equivalent sort of battery solution. So your payload is increased. And then if you're running those big equipment, typically you're going to have set routes. You're going to have a depot or infrastructure where you come back and you're refueling in your own station or along set.
Yeah. So essentially, as you rightly pointed out, no silver bullet to this particular problem. One more topic I wanted to talk about here, and this is again a little bit left field. You've actually gone ahead and developed your own dyno, and this is interesting. Most people, when they're in the market for a dyno, look at the manufacturers who are out there and buy one. What was it about your situation that led you to actually developing your own?
Probably equal parts sort of naivety and sort of wanting something a little bit different than what was on the market. Yeah, we sort of looked at what we were using, I think, at the time, which was a land and sea absorber, which was fine. The absorbers worked quite well for us. The control system didn't really let us do what we wanted to do. At that point, we'd had quite a lot of familiarity with various Motec products, with the ADLs and using them as controllers, M1s, different applications. So really sort of Nick put a lot of time into programming up the ADL to be a dyno controller. That actually worked very well. We could do steady state, we could do ramps, really sort of do whatever we wanted on the control side, and then sort of program that very quickly. Double benefit was then we had access to the logging from the ECU coming into the ADL. We had the power of I2 to analyze everything. We were sort of really liking that for a development sort of role. We ended up wearing out sort of that absorber. We wanted to sort of then run higher RPM engines, higher power engines. So we're like, okay, couldn't really buy anything that suited what we wanted to do. So we sort of did a bit of reverse engineering and a bit of our own idea into developing a new absorber, which had worked well. Then we hit the next limitation where the control valves were a stepper control valve, which weren't really fast enough or no feedback. So after a couple of loops of iteration, we've developed our own servo control control valve for the outlet and the inlet to the water brake.
So this is, just to stop you there, this is a water brake power absorber?
It is a water brake, yes. Yep.
Okay, and maybe just worth talking momentarily about what that power absorber is and the different technologies. Obviously, water brake is one of them, but the different technologies available. Can you speak to that?
Yeah, I mean, the water brake is really just sort of tried and true for your really entry level sort of workshop engine shop, in that relatively inexpensive, and you can absorb a lot of power in a fairly compact, cost effective machine. All you've really got to do is supply the absorber with water at a suitably low temperature and a suitably high pressure, and you can absorb a lot of power. Downside is the finesse at which you control the dyno isn't to the degree at which, say, your top end dyno, which might be a big AC dyno, might be able to do. In the middle, you've got sort of eddy current, which gives you high control, high precision, but the power absorption capability is a little bit limited. With the big AC dynos, yeah, sure, you can have 1,000 horsepower, high RPM, and control to within 1 or 2 RPM, but for us, a bespoke AC dyno system, you're talking millions of dollars, which we're certainly under no illusions that we're close to the capabilities of the AC dyno, but we're found by developing our own control system, our own sort of fast-acting servo valves, we're quite happy with the degree of control that we can do, and then that's allowed us to do some degree of racetrack lap simulation. We can program in a set speed. We're controlling the throttle of the engine as well as the absorber controlling the engine speed. We can set in a profile of, say, Gudaseka is one that we've done, and really have the engine sort of running through, simulating gear changes. We can't simulate motoring the engine. We need an external power source to do that, but we really approximate that by a degree of trailing throttle to keep the RPM up.
So I think that what you've kind of done here, by the sounds of it, is develop a transient dyno, which the Formula One teams and teams at that sort of level use for simulating full race performance. Not quite there, maybe 90-95% of a transient dyno's operation for cents on the dollar.
Yeah, we'd be getting, I don't know if we'd be at 90%, but we'd say we're pretty close to there. But yeah, certainly in a fairly cost-effective and sort of, it's a very useful tool for us. It's very focused on what we want to use it for.
Yeah, conventionally, I'm using a dyno to optimize power and torque, and those are the sort of elements that I'm monitoring. Obviously, there's another bunch of metrics that come along, both from the dyno as well as the ECU or dash logger that I'm using for that particular project. But these are traditionally steady state conditions, and I'll ramp through all of the different zones that I want to optimize in terms of fuel and ignition cells, and you can hold the engine nice and stable in a cell. If you increase the throttle, obviously then the engine produces more torque, which would traditionally, all other things being equal, mean that the engine RPM increases, but the dyno is then going to apply more load to hold the RPM consistent. So that's steady state tuning. And then we'll also do ramp runs where we'll accelerate from, like I said before, maybe 2,000 to 8,000 RPM and log that, and we'll get a nice pretty picture of our power and torque so we can kind of see if for a change if we're going forwards or backwards. How are you using the sort of semi-transient nature of the dyno you've produced to be able to replicate, as you said, a lap around Laguna Seca? Is this more in terms of seeing if your one ramp run actually translates to good control over fuel and ignition around a full lap, or are you looking at this for engine durability testing, all of the above?
A bit of both, really, and we'd certainly start off exactly as you described. That sort of gets your calibration really in the window. You know what the engine performance, the power, the torques are going to be under those situations. What we have wanted to learn after that is, okay, we know the engine makes this power, this torque. How long can it make it for? We don't want it to be half an hour. We want it to be continuous over a long period of time. So to do that, you just have to get miles on the engine under controlled and observable conditions. And certainly, when we're looking at engine temperatures, exhaust temperatures, we find that just doing 1 or 2 ramp runs, you certainly know we're close to having sustained, stabilized temperatures. So by doing the long runs, your 15 minutes, 20 minutes, half an hour running around the racetrack, you're just finding for a long period of time, these things just building up, and you'll sort of start to uncover some of these thermally related issues in the engine, which you wouldn't otherwise find just by doing these short little runs. You'll also, we're sort of trying to measure as much as we can on the engine, including things like blow-by. You'll also find under some situations you might have a ring problem, for example. There's high RPM, low load, all of a sudden you'll see your blow-by starts to spike up. And you go, oh, okay, what's happening on there? The rings have lost control, and then it points you into another area of development. At that point, you might be consuming oil because you're not controlling the gases as well as you should do. So for a durability type application, that's something that then you'd have to focus a little bit of attention into.
Yeah. No, I mean, that sounds like an amazing tool, particularly given your engine development. Coming back, just based on what you mentioned there, with the various configurations of the engines you're producing, what have you found as sort of the wear or consumable items, and sort of factoring into that, what does the maintenance schedule for one of these engines look like? How many racing kilometres or how many hours of racing use between overhauls?
It's different for each of our engines. The little 2-litre engine's quite stressed with the RPM that it does. So I think we'd see like a good season of racing out of one of those. You probably 30 or 40 hours, and would be wanting to look at it. You'd be sort of measuring valve springs, look at your piston skirts, rod bearings, that sort of stuff. Just your typical stuff, not dissimilar to what a 250cc motocrosser would do with similar size cylinder, similar RPM. The bigger engines, especially the more production focused ones. The target is really doing 36 odd hours of racetrack simulation, hard use, and have the engine still serviceable and emissions legal at the end of that. So a lot higher standard for those ones.
Yeah, sure. And with the engines that you're selling to customers, are these a return to base overhaul, or are you happy for customers to do those overhauls themselves, or with their engine shop of choice?
Yeah, look, a lot of them end up in sort of far-flung parts of the world in Europe, where the customer can sort of demonstrate they've got a good technical aptitude. Yeah, we're very happy to support them in servicing their own engines where they are. And we do have pretty good documentation for the engines, your build manuals, spec sheets, and that sort of stuff. Generally, we'd like to see them come back as well to get a good snapshot into how everything's been working over the period the customer's had it, and we sort of might keep an eye out for things that they might otherwise not be observant to.
Yeah, a very different situation to your engine development, but back when I was running my shop and racing 4G63 Evo, and because we had some success, I ended up with a bunch of customers kind of doing similar, maybe a little bit lower spec, but it really ramped up my engine development, being able to tear down, instead of just one engine, just my own engine, and sort of see what everything was looking like inside. Now I got sort of 4 or 5 samples, and we could sort of start moving in a particular direction and see the results of that much quicker. So I think there was a big benefit for us in speeding up our engine program, just having more of our customers involved with it.
Yeah, no, we agree too, and we've certainly benefited from that. And as engineers, you love having good sample sizes and good data to look at, and then it sort of really influences us to make sure we're really 100% on our documentation, knowing the spec of each engine that's gone out, what parts went into it, what the clearances, the builds were, so that when you're trying to analyse these observations later on, you've got some metrics you can tie back to.
Perfect. All right, Simon, I think we'll move towards wrapping this thing up. We're sort of getting a little long here, and I do want to respect your time. We've got the same 3 questions we ask all of our guests, and the first of those is, what's next in the future for you and Prototipo?
Well, look, we're sort of really not expanding so much. We're very happy with the direction the business is going in. We've got a really good core team. A lot of exciting projects ahead of us, which have got some miles to run in them that we want to see really become successful. So just heads down, keep working hard, and keep going at it.
More of the same. Next question, is there any advice you'd give to a younger version of yourself, or maybe one of our listeners, that would help you reach where you are today in your career faster, or potentially avoid some pitfalls that you've seen along the way?
Oh, look, I don't know if any advice I give of my experience would be sort of relevant. Everything changes every day, but I guess so. It's just follow what you're interested in. There's no set rules. There's no set career path where if you do this will happen to you. Follow what you're interested in. I've always found a lot of value from having done academic study. I enjoyed university. I enjoyed what I learned and the skills I learned from that. But it's not for everyone as well. Other people have had equally good experiences following other paths. Just follow your own path, work hard, and keep your eyes open for the opportunities.
Yeah, I think the sort of following your passion to a degree, if you can do that, obviously not every passion is going to form into a viable sort of business or job, but chances are that everyone listening to this podcast has a passion for motorsports. So I think we're probably all on the same page there. But, I've said this before on the podcast, the old story, if you can do what you love for a living, you'll never work a day in your life. And I mean, I'd say that doesn't entirely hold water, but for the most part, absolutely it's true. I mean, fair to say that I've had some days where I've been like, what the hell is going on here? I do not want to get out of bed today, but fortunately for me, those are few and very far between. So I'm pretty lucky. I think if you can get to that, you're doing pretty well. Just to cover off the university degree, that direction as well. This is actually something that came up chatting with a few friends over lunch just recently, and I've got a daughter who's sort of approaching the sort of age where a university degree or that option is going to come up. And I haven't gone through university myself, but then also, I feel probably using maybe about 10% of what I actually learned through my degree, I am really torn, and I genuinely don't see that it is the be-all and end-all. I think it's very much down to the individual. So, there's people equally successful with and without degrees. So, as far as my daughter goes, when she gets to that age, I'm certainly not going to be pushing her towards university, but by all means, if she wants to go, I'll back her as well.
Yeah, no, I agree. I think the way I often sum it up is that it doesn't teach you everything, but it teaches you sort of how to learn things, or teaches you, okay, I need to know about this, now I'll go and find it. But certainly not the only way to do that, and there's other ways to get to the same result.
Probably worth adding the caveat again, we're here with a motorsport following, but if you want to be a doctor or a lawyer, you're going to have to go to university. Yeah, probably the exception, not relevant to us. All right, last question for today. If people want to follow you and see what you're up to, how are they best to do so?
Oh, we're pretty old school, really. We just really got our website, prototipo.co.nz or synergypower.co.nz. We sort of just keep away in our little workshop and don't blow our trumpet too much. But we will be putting a little bit more information up as we sort of get some of these new products out and into the market.
As usual, we'll link to your websites in the show notes to make it super easy for people to find. Look, a real pleasure to catch up again, Simon. It has been a number of years. Really interesting to get your more in-depth background and see where you're headed. And we wish you all the best for the future.
No, thanks for that, Andre, and appreciate the opportunity to come and have a chat.
If you enjoyed this episode of Tuned In with Simon, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high-quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. This is also a great place to ask any questions you might have, and I'll do my best to answer them if your review gets picked. So, this week, a big shout out to Quarry Wood from Canada, who has said, and it's a long one, absolute must listen to for gearheads. Unless you've been hiding under a rock, you're probably familiar with this podcast already, but if not, stop searching and dive in right now. The plethora of topics, depth of detail, and breadth of knowledge far surpasses the competition, if you can even call them that. Andre either has a natural ability or a highly developed skill for interviewing very intelligent and experienced auto industry talent. No detail is missed, no savoury subject unaddressed, and each guest seems to feel right at home each time. Incredible. Well, thanks for your kind words there, Quarrywood. You've also got a question, and that question is for a sucker with an ECU in his daily that has to be bench flashed, no OBD support, and no readily available tuner support via HP tuners, etc. Is my only option learning to use WinOLS? Well, I wouldn't say it's your only option, but it probably is a very viable one. The alternative, of course, sell it and buy something that's a little bit better supported in the aftermarket. But I'll leave that choice to you. If you do decide that OLS is the direction you want to go in, remember we do have our WinOLS Mastery course available. You can find that in our courses section on our website. Anyway, thanks for the kind words there. And if you get in touch with your t-shirt size and shipping details, we'll get a fresh tee shipped straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get 75 $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.